Hello, this is John from caveofprogramming.com. In this tutorial we're going to take a look at vectors and memory. In this tutorial I'm probably not going to give you any kind of practical exercises, but this is just stuff that's really worth being aware of, and you can certainly try it out if you have the motivation. So one thing I want to mention from the last tutorial is that we've got two ways here of iterating through a vector. One looks very complicated and uses an iterator, and the other just uses a kind of index-based loop. And you might wonder, given that the index-based loop looks a lot simpler, do you ever need the iterator version here? And the answer is that using an index-based loop to iterate through a vector is not necessarily less efficient than using the vector. So if you just want to iterate through it, you don't necessarily need an iterator. You can use for example, a const iterator to ensure that the elements can't be changed using that iterator, which can be useful because, of course, here you can always change the elements, and you can here as well. But the vector provides us with methods to get a const iterator, which would ensure that we couldn't change the elements. So there can be an advantage to using an iterator, at least for that reason. And it's important to be aware of iterators, particularly because you'll need them when working with other members of the STL library. And of course, as we've seen, they have their own particular uses here, but you don't necessarily need to use them for iterating through the vector. Now, C++11 introduces a way of iterating through a vector that is particularly nice and simple, but I'm going to put that in a different section of this course because it's 2014 now, and I think not everyone is using C++11 yet. So I thought I'd put the C++11 stuff in a separate section of the course later on. But it does give us a really nice way of iterating through a vector, which is worth knowing about, but we'll look at that later. Let's close this project because this bug in CDT with the overloaded endler thing is quite annoying. So I'm going to close that, and we'll create a new project here. So I've got this project, not this one, I've got this project on vectors and memory already created here. So I've included vector here, and I'm going to declare a vector. Let's make it a vector of double, and I'll call that numbers. Now, one thing you can do is you can pre-size your vector if you want. So here I could specify an argument. Let's make it 20, and then let's output here the size of the vector. So I'm going to say numbers.size. And if we do that, we find that we've got a pre-sized vector with 20 elements. Now, a vector manages an array internally, and if you add more elements to the vector than that array can currently accept, what the vector class will do is it will create another array that's bigger, copy all the elements to it, and then you can carry on adding elements. So to show you that, let's create a loop here. Let's say for int I equals 0, I less than, let's say 10,000, I plus plus. The vector actually has a method called capacity. So we can say int capacity equals numbers.capacity. And what this is it's the size of the internal array that the vector is using, and that size is going to increase as you add elements, but it's going to increase in steps. So let's output here capacity, so capacity, and I'm going to add numbers.capacity. Well, in fact, let's just output this capacity variable here. So I'll run this just so we can see it. So the capacity here is 20. We've reserved, we've pre-sized the array to 20 elements. So we've got a capacity of 20. And by the way, you can also supply an initial value for those elements as well in the next argument. So this would give us a vector which has a size of 20, probably a capacity of 20, and every element is initialized to 1. But I won't make use of that here, but it's useful to know. Or you might want to initialize all the elements to 0, of course. Now, to investigate how the capacity changes as we add values to the vector, let's do numbers.push back. Let's add I there. I is an integer, but of course we can. It can be easily typecast to a double. We don't even need to have to put an explicit typecast in there. Let's say that if the capacity changes, so if numbers.capacity is not equal to capacity, then we're going to update our capacity value with the latest, so numbers.capacity, and we're going to output it. So let's just copy this. So this gives us a little program that outputs the capacity whenever it changes. And if we run this, what we find is that the capacity increases exponentially with the number of elements in the vector. If we actually pre-size it to 0, like this, and run it, then we're going to see here that for this implementation at least, it's actually doubling every time. It's worth trying that on your system if you have the enthusiasm. And the idea is that if you've got a very big array with lots of elements, you're probably going to add lots more elements to it. There's no way of knowing, but that's a fair assumption. So it's no use creating a new array internally every 10 elements if that vector's already got 1,000 elements in it, because if it's got 1,000 in already, it's a fair assumption that you might add another 500, and for that reason the vector increases the capacity by actually creating a new array and copying the elements from the old array to it in a way that depends exponentially, that like the size of the new array that it creates depends exponentially. It increases exponentially as you add elements, so it's the size of the new array is, I guess, proportional to the number of elements in the array, I should say. So so this is worth being aware of, and it helps to ensure that the insertion time, the time it takes to insert an element into the vector, remains as constant as it possibly can. So if you insert an element into a vector and it has to internally create a new array with a bigger capacity and then copy the elements from the old array to the new array, there's going to be a brief pause in your program, and you want those pauses to appear as little as possible, and that's why it tries to kind of guess how big your array is going to get based on its current size, and it increases the capacity based on that. So the capacity is completely different to size. The capacity is the size of the internal array that the vector has reserved. The size is the actual number of elements that you've added to that vector. Now, if you Google for something like STL vector, you get a lot of very useful reference pages that show you all the different useful methods that you can use. There's maybe like 2 or 3 that I want to kind of highlight here. One is that there's a clear method, so we can say numbers.clear. That's just going to remove all the elements in the vector. But if we look at how that works, so let's get the present capacity here. So numbers.capacity. So that's going to affect the size. If you clear the vector, it's going to have a size of 0. We see it's got a size of 0, but the capacity hasn't changed. So changing the size, the number of elements in the vector that are considered important, doesn't change the capacity of the internal array. You can change the capacity of the internal array downwards if you have to, but you need to do that by reinitializing the vector with a new temporary vector, and it's not something that you typically often have to do. You can also you can there's a method called resize that actually resizes the vector. Let's resize it to 100 elements. So clearly we're gonna discard a lot of elements when we do that. Now, as far as I know, that no implementation will actually discard those elements. So you've still got the existing elements in there. So if we output numbers, for example, let's output numbers 2, which should be 2, because we added 2 at index 2, and we run this, we're still going to find we've got 2 in there. So that's not going to affect existing elements. It's just changing the kind of size internal variable of the vector. It's changing it up or down, just as you like. It's not going to affect the capacity at all, so it's not altering the internal array. It's just purely changing whatever it is in the vector that stores the size of the vector. So if you resize it, then size will give you a different answer, but the capacity remains unchanged. There's also a reserve method. So reserve is not, it shouldn't have any effect if we say that we want to reserve memory in the internal array of the vector for a value less than it already has. So the idea behind reserve is to increase the capacity, in other words, increase the size of the internal vector of the array. So if we've got 10,000 elements in there and we try to reserve 100,000 and we run this, we're going to see that the capacity, the size of the internal array there, has now increased. So the internal array is bigger, and the size of the array here is still what it is originally. So this is 10,000. The capacity is now 100,000, and we can see, because we've still got the original elements in the vector, we can see that it must have copied our old elements to the new array, which has our new capacity. So that's it for this tutorial. There's basically just those two things there, size and capacity. And size, you can resize with the resize method. Capacity you can change with the reserve method. You can also specify an initial size for the array. And the size is purely a kind of internal variable in the vector that keeps account of the number of elements in it. The capacity you don't usually have to bother with, but sometimes for efficiency you might want to get in there and meddle with the actual size of that internal array of the vector to avoid these reallocations to new vectors that have to occur necessarily if you keep adding elements beyond the vector's current capacity. Okay, so that's it for this tutorial. I won't give you an exercise here, but of course if you feel like experimenting with this, of course that will repay your time. It's well worth doing. But we'll leave it there for now, and until next time, happy coding.